Hi, this is Ling Fan. I'm a professor at the University of South Florida. I would like to talk about Julia Admittance, a package we are developing. This video is for Juliacon2020 Light Talk. First, why do we need admittance? For power grid, we usually like to do stability analysis, and we can split a system through a bus, and looking at the system from left and right as a two component, and each can be impedance or each can be admittance. With that, we have their frequency domain response. We can conduct stability analysis using Nyquist plot or Bode plots, this kind of criteria. And this method has been widely used in power grid industry. For example, this is the task force called Wind Energy System Subsynchronous Oscillation Report by IEEE Power and Energy Society. It's called TRAD. So what is admittance? I like to just give a quick tutorial. If you look at ILC circuit that Professor Lewin put on the blackboard, here he can write ODE equations for this circuit by express voltage and current relationship. The highlighted one, it is Z, and that is impedance. Express this voltage and current relationship. So this impedance actually has a lot to do with dynamic of the systems. So first, let's just solve this guy in this Julia doing time domain simulation, use differential equations and using plots. And we can quickly see that this is great to see that you can show this 40 Hertz oscillation for excitation. In this case, we perhaps give a step response for the incoming voltage source. Then the current is have 40 Hertz, and also the capacitor voltage has 40 Hertz. So how can we show it in the impedance? So we can plot impedance and impedance in the frequency domain. You can see there's a dip at 42 Hertz. So this 42 Hertz, in fact, it actually matches this 40 Hertz because it means, yeah, this is very low. So any kind of voltage turbulence, you expect to have a big current at this frequency. So therefore, we have this thing called subsynchronous resonance in power grid or ILC resonance. So this impedance is what we want, the frequency domain response. And this is a scalar one, and it can be measured. So how? We can use frequency scan or harmonic injection method. So next page, we are going to show a more sophisticated matrix admittance example and also show how do we do harmonic injection. So this is an example of 2.3 MVA battery inverter. Now we are going to put in admittance. We want to look at admittance. So first, this guy is three-phase. It will be connected to a controllable voltage source. Everything is high power, high voltage, so you have to have very special equipment to do that, and that this experiment is done at National Renewable Energy Lab. So for three-phase voltage, we usually use DQ to ABC, and for current, also ABC to DQ. Essentially, you can see the voltage current are expressed by a matrix relationship. This is called DQ admittance. It's 2x2 admittance. At every frequency point, you can see there is a value here, or matrix here. So how did we get this? We first give VD a perturbation, and then we all record ID, IQ. Then do FFT analysis for this steady state sinusoidal disturbances. So we got the first column and do the ratio. So we got the first column at this frequency. Next, we put the VQ, got the second column. So in the end, we got something like this right part for different, something called operating condition, that different real power, reactive power condition. We can grab the entire frequency domain responses for this guy. It is the admittance. All right, so now what is the most important stuff in this procedure? That is, it's a very data intensive. Previously, people usually use Python, and the real have package to do Python. A lot of people do Python. So here, I tried Julia and found it is great. So essentially, we just have lots of time domain data we have to read in and lots of frequency points. For example, in this case, we have to have two events, like one disturbance, another disturbance, and then we can take care of ID, IQ, so two channels, two events, two channels for, let's say, 39 points. So you can imagine you have so many of this data to handle. And in case you have a big network system like a 3-bus, then it is much more. So this is just a 1-bus system. You have 2x2. All right, so then you can imagine you have lots of data, you have to read data, plot data, and use this plus JL delimited file. We can push data, everything into a data structure, voltage current there. Finally, then we can just use FFTW, the package, really nice to grab the phasors out, phasors of voltage current. And the last step, this green part are not data intensive. After you have phasors at each frequency, just grab their ratios to got admittance at this frequency. Following up, you can also do data fitting, get an S-domain expression. With S-domain expression from source and load, you can also do stability analysis. Some people have written this control system.jl. So the blue part is really cool that can be handled by Julia very well. So I'll give you an example here. We do 3 bus, 39 frequency point, about 6 event, because each bus is DQ, so you can have to have the 6 event and 6 channel, 39 data point. And because the software gave us lots of channels, so entirely we have to handle 1.4 gigabytes of data. For example, this is one event at one frequency, we have a folder. Inside the folder, we have this much of data. Every data is 2.7, but you can look, they will have multiple data here because we have lots of channels. Each 2.7 megabytes data, you can see it's like this. First column current, first column is time step, and then 10 channel data. So this package can be really nice using delimited file. You can read this file and read multiple files one by one. Read all these files. Finally, we can stack everything into a data structure. Here we use data total all frequency, array after array, array over array. So it's necessary to create a bigger data structure to save all time domain data for every frequency measurement, every channel, every event. So with that, then let's go to FFT. So here is just an FFT function that is pretty nice that you can find from a lot of demo of Julia. So with that, then we can just keep calling that for each event, each channel, each signal. So then we got these phasors at every measurement that we want. So that's a very interesting one that we can finally grab the booty plot here. We finished this step that is called grab phasors. So that's what we found. It is really nice, great to deal with data intensive applications, and several packages, this delimited files, FFTW, are pretty handy. So thank you.